final session of our summit today, and it's my honor to welcome our next speaker, who will be having a session on the topic energy integration through process efficiencies. May I please welcome Mr. Yashodhan Mankame to the stage with his team. And let's give them a huge round of applause. This is the last session, everyone. Mr. Yashodhan is the Executive Vice President, Business Development, Praj Industries Ltd. A very, very warm welcome to you. You can join us on stage. Please come. And he holds a bachelor's degree in chemical engineering. He has 34 years of experience in the bioenergy and renewable energy sector, including 25 years in international markets. He currently leads business development for the bioenergy vertical for India, Southeast Asia, Africa, and Europe. His role is instrumental in driving the global expansion of Praj's bioenergy portfolio. His expertise is in business project development, from project conceptualization to commercial operation for bioenergy projects, beverage, industrial-grade ethanol projects, and wastewater management solutions. He has been involved in the development of 100+ bioenergy projects globally and has presented papers in multiple international conferences and business forums. A very, very warm welcome to you. Everyone, can we have a huge round of applause for our final speaker for the day?
Thank you. Good evening, friends. First of all, thank you to JEMA for inviting me to speak at this event. And thank you to all of you here to wait for this last presentation. So the topic I'll be speaking on is energy integration and process efficiency. My name is Yashodhan Mankame, and I represent Praj Industries Ltd. With me is my colleague Himanshu Taneja. Himanshu heads our business in northern India. You must be knowing about Praj, but to give you a brief overview of Praj Industries Ltd. We are a company specializing in technology, engineering, and supply of projects for bioethanol and in bioenergy space. We do ethanol plants from any kinds of feedstocks, first generation feedstocks, which are either sugar-based or starch-based, and also second generation feedstocks, and also for all kinds of products, whether it's fuel-grade ethanol, beverage-grade ethanol, industrial ethanol, and pharma or cosmetic-grade ethanol. Apart from that, we do CBG plants, biogas plants, and many other systems, which are engineering and process systems. Praj, over a period of in the last 40 years, we have more than 1,000 ethanol plants worldwide, which are based on Praj technology, and have references now, I think, in about 104 different countries. So today, the industry is facing many challenges. Industry challenges are, of course, rising energy cost, rising feedstock cost, and water scarcity. Now, to overcome these challenges and to maximize profitability, what the industry can do is, of course, on one side, increase revenue by capacity expansion, multi-feedstock operation, round the year consistent operation, and revenue from co-products. On the other side, of course, they can reduce cost of production by achieving energy and water reduction, increasing process efficiency, and reducing and recycling of waste streams. What I'll be speaking on today is reducing energy cost. So basically reducing energy and water in your ethanol plant. The starting point of reducing consumption of energy is to have accurate measurement. in a total ethanol complex, it is very important to measure energy production and consumption, starting from the boiler. From there, how much steam is going into the turbine, at what pressure, how much is the internal consumption of the boiler, so how much steam is going back to the deaerator and at what pressure, and finally how much steam is going to the process plant. So it is very important to measure the consumption at each of these points. So having measurement devices like flow transmitters, pressure transmitters, to properly understand the consumption points in the plant. It is also very important that you should be measuring how much steam is actually going into the process plant, which is, at every process plant has a steam header. So measurement of steam going into the steam header, both in terms of flow as well as pressure, is again very important. And then beyond the steam header, how much steam is going into all the consumption points. So it is very important again to measure the steam flow and pressure at all the consumption points. So to optimize steam consumption in your plant, as I said, accurate measurement of steam at every consumption point is important. So having measurement devices to measure this is also very important. Also, what an ethanol plant can do is also to look at the balance of the hot streams and cold streams in their plant, and having recovery of heat. So the cold streams should be used for recovering heat from the hot streams, and wherever there is a heat exchange possible, that should be done, so that there is maximum recovery as well as preservation of energy. And the third point, which is very important, is to plug any kind of energy losses. What we have seen in many plants is, when the plant starts up, there is a set point set for energy consumption and temperatures. Over a period of time, those set points change. But people are not bothered to understand why the set points have changed. The set points would change because there is something happening in the plant. So it is very important to do a root cause analysis of that, what is happening in the plant, so that this higher energy consumption can be plugged, and so that the energy can be reduced. So yes, it is also important to know where you are having energy losses and plugging those energy losses. Add-on benefit of steam saving. Steam saving is equivalent to water saving, because when you are putting steam or heat energy in, you would require to take out that heat energy. And to take out that heat energy, you need water. So whenever you save heat energy, you are also saving equivalent amount of water which is required to take out that heat energy. So it has a dual benefit. You save steam as well as water. Now I'll go to, there has been a continuous development as well in achieving lower steam consumption. Now, if you look at an ethanol plant, olden days, if you look at ethanol plants which are 7 years, 8 years, more than 7, 8 years older, for a typical rice-based ethanol plant in India, the steam consumption used to be somewhere at around 3.9 or 4 or 4.2 kg per liter. Then, of course, there were integrations in the plant where people went for, and now which has become a very conventional plant, is dryer vapor integration to recover energy from dryer. So in a typical rice-based ethanol plant, which includes a DDGS dryer, in a conventional plant which has dryer vapor integration, the consumption of steam is about 3.4 kg per liter. This is at about, for a plant which is operating at about 13 to 14% alcohol concentration. Then to further save steam, there is a technology called evaporative distillation, which would reduce the steam consumption from 3.4 to 3.1 kg per liter. For further saving, there is MVR technology, which is MVR being used in in the evaporation plant, which would further reduce the steam consumption to 2.7 kg per liter. Then you have an option of using MVR both in the evaporation plant as well as MVR on drier vapors, which would then reduce the steam consumption to about 2.3 kg per liter. And then, of course, the final saving can be achieved where you, apart from the evaporation MVR, you also put a MVR in your distillation plant, which can further reduce the steam consumption to 1.7 kg per liter. And as a technology provider, we are supplying these kind of plants both in India and in overseas market. So this is for a typical rice-based ethanol plant. When you move to a corn-based ethanol plant, of course, corn-based ethanol plants operate on a lower alcohol concentration, so they consume more energy. So if you compare this, this is for a rice-based ethanol plant, and this is for a corn-based ethanol plant. So there will be about 0.3 kg per liter additional steam required in a corn-based ethanol plant. Now I'll run through the aspects of these different technologies. So this is a dry grind, typical conventional grain or rice-based ethanol plant, which has consumption of steam in liquefaction, distillation, evaporation, dehydration, and dryer. And then there is heat integration between the dryer and the evaporation section. So typical steam consumption here is at 3.4 kg per liter, and the steam used is at 3.5 bar. Generally in India, we use steam at 3.5 bar. Unlike overseas market where steam is used as a higher pressure, overseas market you use steam at 6 bar or 7 bar, because most of those plants operate only on corn. So when you're operating on corn, you can use higher pressure steam, 6 bar, 7 bar, both in distillation and dehydration. However, in India, you have plants which operate both on corn and rice. And rice is a more delicate raw material if you compare it with corn. So when you use higher steam pressure on a rice-based ethanol plant, especially in a dryer, then there is a risk of damaging the DGS quality. So that's why in India we use a lower steam pressure, and we don't have what we call a split distillation in the Indian market. So this is for a conventional ethanol plant. Then we go to evaporative distillation. Evaporative distillation is a scheme where you use a evaporator, a pre-evaporator before the mash column, so that there is heat integration between this pre-evaporator and the mash column. So this is a technology that can be used for new ethanol plants, as well as this is a technology that can be used for reduction of steam consumption in an existing ethanol plant. So to reduce steam consumption on a unit basis in an existing ethanol plant, this is an excellent technology where what you are achieving is about 30% reduction in steam consumption. But in addition to this, what you can also achieve is a 30% expansion in your capacity. 30% expansion in your capacity in the distillation, and by using a technology called MaxMol, achieve a similar expansion in your capacity in the dehydration section. So this is, apart from new plant, this is an excellent technology for expansion and steam saving and an existing ethanol plant. Of course, this is a Praj is a process patent for this technology. In addition, of course, since you are achieving expansion and steam saving by using evaporative distillation technology, you will have on a unit basis lower spent wash volume, and this can be done, or this can be achieved in an existing ethanol plant by minimum add-on hardware. So in that, as I said, evaporative distillation, you would have steam consumption of about 3.1 kg per liter. Next is, of course, the concept of MVR in evaporation. MVR basically what it does, it compresses vapors, and by compression of vapor, it increases the temperature and pressure. So what you're doing is you're using the heat energy available by compressing that those vapors. You are reusing this heat energy. So MVR used in evaporation plant. So the vapors in evaporation are compressed, heated up, temperature is increased and taken back to the system. So what you need is initially only startup steam for the evaporation, and then it actually uses the same heat that is available. So with this using MVR in evaporation, you can further reduce the steam consumption to about 2.7 kg per liter. The next stage, of course, is using MVR in the evaporation section, but also in addition to this, using MVR on the drier vapors. So you have MVR, as I discussed in the earlier slide, on the evaporation section, but you have also MVR on the drier vapors. So you have dryer, you take it to a direct vapors, you take it to a direct contact condenser, pass it through MVR, and then those vapors can be used in the distillation section as heat input. So here in this, what you're achieving is a steam consumption of about 2.3 kg per liter. So further reduction in steam consumption. And then, as I said, the maximum steam saving that can be achieved is by using also an alcohol MVR. The earlier technologies that I have explained, those are the technologies which we have executed in India as well as offering in India. Alcohol MVR is something which we have still not offered in India. This is a technology which we have only used in the overseas market. So apart from using MVR on the evaporation section, also in the drier vapors, we use now an MVR also in the distillation plant. So the vapors that are coming out of the rectifier column are then passed through a MVR, which is an alcohol MVR, and compressed and then reused back in the mash column as heat input. So at this, what we are able to achieve is a very low steam consumption of about 1.7 kg per liter in the whole complex of an ethanol plant. So that's on steam saving. Apart from using different technologies for steam saving, you can achieve steam reduction also by increasing alcohol concentration. So typically for a rice-based ethanol plant currently in India, which operates at about 13 to 14% alcohol concentration, which I call as a conventional plant, the steam consumptions range from 3.2 to 3.4 kg per liter. Now, if you're operating at a lower alcohol concentration, then of course your steam consumption increases. But now there are newer E-strains available which help you to also operate at a higher concentration. So just by increasing 2% alcohol concentration, if you go from 14% to 16%, you can achieve another 0.3 to 0.4 reduction in steam consumption. Now, if you can go further beyond from 16 to 17%, you will achieve further reduction in steam, because then you have lesser vapors of alcohol to evaporate. So that's another aspect which is coming in technology as far as steam saving is concerned, is increasing the alcohol concentration in your fermentation plant. Now, so that was about saving of steam, and whenever you save steam, as I said, you will be also able to save water. But saving of water is again becoming very important. So there are technologies which are available, which is air cooled heat exchangers that can be used for saving water in your ethanol plant, especially in some parts where there is water scarcity. Also environmental during environmental clearance, there are very stringent norms being put by the agency for water saving, and wherever there is a very stringent water saving norm, you can use ACHE as a technology for saving water. Basically what an ACHE does, it uses ambient air to cool for the cooling purpose, and that with that you can achieve saving of, and so the overall water consumption in your plant can be as low as 3 liters per liter. So this is a typical water saving that you can achieve in a, say, a 200 KLPD plant by using ACHE. You can achieve almost 60% water saving in an ethanol plant by achieving using ACHE. And since you're using ACHE, you are not using you have a lesser load on the cooling tower. You will also achieve power saving of almost 8 to 10% in the plant when you use an ACHE. So that's about steam saving, energy saving, and water saving in an ethanol plant. And thank you for your patient listening. And if you have any questions, please. Thank you.
Consul, can you check for the mic, please?
सर, आपने MVR टेक्नोलॉजी की बात करी है, तो इसमें पावर कंजम्पशन कितना बढ़ता है? Does it match with the total package?
Now, typically for when you are using MVR, especially for Indian condition, what we have seen is the steam power starts balancing for a capacity beyond 300 KLPD. So up to 300 KLPD, it is difficult to balance the steam power, but once you hit 300 and above, the balancing is possible.
With which pressure boiler?
So usually for capacity range between 350 KLPD to 400, 450 KLPD, one needs to go into 88 kg pressure, and the additional power consumption is around 700 to 800 kilowatt for a 350 to 450 KL capacity. Beyond 500 KLPD, then there is possibility of balancing it even at 67 kg. But then nowadays, since CO2 also is becoming equally, in a framework of whatever plant capacity is in proportion to that, one has to go for CO2. So CO2 itself requires about another 1 megawatt, generally for 500 KLPD and above. So again, at 88 kg, it balances very easily.
Nicely, yes.
And fuel consumption goes up by about 1% in terms of 67 kg versus 88 kg pressure. The fuel consumption will go just by about 1% higher, but then you have 33% reduction in overall steam consumed in the plant. So from, let's say, 3.2 kg level, we are bringing it down to 2.3 kg level. So this is almost 33%, 34% saving in overall fuel being consumed in the plant.
Correct. Sir, you are talking about 3.2 or 2.3 kg. Is it 3.5 kg steam or 11 kg steam or 66 kg steam?
Ours is all sized for 3.5 kg gauge pressure,
Yes.
saturated steam at 147 degrees.
This is what
See,
is it?
yeah, again, the reason which I mentioned during my presentation why it is size as 3.5 bar is, in India, you have plants which operate both on corn as well as rice.
Yeah.
When you're operating on corn, you can use higher pressure of steam, both in the dryer as well as in the distillation system. So you can use about 6 bar, 7 bar steam. But when you operate on both the feedstocks, rice is a more delicate feedstock. So if you are using higher pressure, higher temperature of steam on rice, then you would damage the DDGS quality. And that's the reason you need to use lower pressure at about 3.5, maximum 4 bar as far as the Indian conditions are concerned, because you need the flexibility to operate on both feedstocks.
Right. So thank you.
If
Another
you're
question.
operating, that is, if you in the overseas market where we operate using only corn, then when we use 6 to 7 bar pressure steam, then we don't go for MVR. You use what is called as a split distillation, which is further integration of heat between distillation columns, where in some cases we don't use MVR also.
Fine, sir. Another question is that you are saying the air condenser, air coolers, are they working 24/7, 365 days, or it needs some cooler atmosphere?
No,
Because
it works the whole year. We have one which.
So we have an installation very close from Delhi. It is in Indian Potash Limited, where we have achieved overall water consumption of 3.5 kg per 3.5 liter per liter. Even when they produce ENA, the water consumption doesn't go beyond 4 liter per liter.
So it's very, very
So
close
this plant
to
is running for almost 3-4 years now, and they operate almost 330 days a year.
always
Throughout
on
ACH.
air coolers.
Throughout on ACHE. Over there we have used the type A ACHE. However, nowadays we are also looking at type H ACHEs. So these are two different models, but then they work around the year.
Okay.
But currently, mainly ACHs have been used in India where there is water scarcity. So that's a driver.
But only thing is when you go in the heated portion of the country, like down south or there you don't get the ambient temperature which can give you 32 degree.
Sir, here we have designed at the ambient temperature of 45 degrees Celsius. So there is no problems.
See, the only concern is the coastal region where there is high humidity. ACHE has a challenge where the temperature and humidity both are high. So apart from the coastal region, we don't see any challenges anywhere in India.
Okay, sir, thank you.
The ACHE is also employed in the distillation side of the condensers, not on the fermentation side. So we have Abhinav.
See,
Monsoons.
yeah. No, rainy seasons also we have seen like the one which is very close to Delhi. It's operating perfectly fine.
Hi.
Because in the rainy season also the wet bulb temperature does not considerably change. The wet bulb temperature is normally for a region remains.
Like winters also it works fine. Winters, rainy season, and in coastal, what is the reason? Like it's moist air or what?
It's basically moist air.
So during rainy season also will be the same issue.
It doesn't. If you even see interiors of India, also during rainy season you don't have very high humidity. You don't sweat when there is rain. If you go to a coastal region, there is high humidity and you sweat. So that's the difference.
Typically, sir, we are shifting from water-cooled cooling towers to air-cooled cooling towers. Typically for a 200 KLPD plant, the differential investment could be anywhere between 3.5 to 4.5 crores. Typically for a 200 KL plant. Yeah.
Hello. Yeah. Extending to same question. As you said, conventional plant has consumption of 3.4 kg steam per liter. And now you are saying the newest technology with 1.7 kg per liter. So what kind of capex difference you think for this?
Actually, 1.7, we are not really aware of capex differential for in the Indian market. We have done it for the overseas market, but we can give you a capex differential between, say, conventional and 2.3 kg per liter. So typically, as I said, this is done for bigger capacity plants. So we did that for a 500 KLPD plant. Differential is somewhere around 45 crores for a 500 KLPD plant. 45 to 48 crores, somewhere around that.
So do you mean that this kind of technology is good for only these kind of big plants, 500 KLPD, or can be good for medium size, 200, 300?
No, as I said,
plants?
earlier, this kind of plant start becoming viable once you go beyond 300 KLPD. So we wouldn't recommend MVR technology for anything which is below 300 KLPD.
See, in present configuration, it has become essential to add carbon dioxide plant, which is a power consuming unit. Additionally, for MVR, there is an increment of 700 kilowatt to about 2 megawatt sometimes for different capacities. So this differential power has to be met from the consumed steam and not any surplus steam. So our idea is not only to reduce steam, our idea is to reduce fuel. So we have to balance steam and power for these incremental, add-ons which are coming up with newer configurations in grain plants. And therefore we have, arrived at some understanding that beyond 400 KL, beyond 350 KL, the balance actually can be achieved. Below, for smaller capacities, it is not viable.
Thank you.
So would you like to ask a question? No. Anybody else? Any questions from the audience?
Sir, I would like to add, like for typically a 500 KL plant, the consumption of steam for rice case would be about 63 to 64 tons. And something similar for even corn. Corn would be about 65 to 66 tons per hour steam. And the power consumption is in the range of about 9.5 to 10.5 megawatt. So this is the balance which we can achieve at about 88 kg pressure. Coming, down to about 4.5 at the exhaust.
Balance is out for, MVR system.
Any more questions? This is the final session for the summit. Everyone seems pretty content. All right, thank you so much for the final session for today. To Mr. Yashodhan and his team member.